Good day and welcome to your Unit 11 lesson. Actually, today we're going to do a 3-in-1, so we're going to cover 11.1, 11.2, and 11.3. So Chapter 11 is about equilibrium, chemical reactions that are at equilibrium. Let's start by defining what an equilibrium is. So you're used to using this word for a static equilibrium, which we have here. So something that is just piled up and not moving, for example. If I'm standing on a leg and I'm not moving, well, I'm at equilibrium. Okay, so that would be normally the way we use the term. Now, in chemistry, what we call, when we talk about equilibrium, we're talking about a dynamic equilibrium. What do we mean by that? It's that it looks as if there's nothing happening. It looks as if the reaction is over, but yet there is still something happening at a microscopic level. Just think of a scale, for example. If I have an old style scale that looks about like this, right? And I have a piece of wood like this across, and I start putting objects on this side that are of equal size and equal weight, and I keep adding some on both sides at the same time, because I have two hands, right? So I can do it at the same time. Well, if I do it perfectly, my scale won't move. It'll look as if it's at equilibrium, it's balanced. And yet, I am posing an action. I am adding objects on both sides. So there is something happening. Well, we can talk about an equilibrium in chemistry in these terms. So there is still a reaction occurring, but because actually there are two reactions that are opposite that are occurring, they're canceling out and it looks as if nothing is happening. So it looks as if the system is at rest or the reaction is over. So let's look at examples. The first one would be a physical example, so a change of state. If you look at the water bottle over here, there is a section at the top that is filled with air, and there's the water over here. Now, it looks as if, because the water bottle is sealed, it looks as if nothing is happening, when actually the gas particles here are condensing, so they are becoming liquid and going into the liquid part here, and some of these liquid particles are evaporating, and those two reactions or changes are happening at the same speed, at the same rate. So they're canceling out in a sense, and it looks as if the volume in my water bottle is not changing. It looks as if the bottle is sealed and nothing is happening inside. And yet at the microscopic level, there is something occurring. So that's the first example. Another example of equilibrium would be a solubility equilibrium. So if I dissolve something in water, here we have cubes of sugar that would be put into tea. It could be salt in water, it would do the same thing. So my cubes of sugar are clumps of molecules of sugar. The clump is so big that we're actually able to see it, and when we put that in the tea, well, the particles of water separate the molecules, and because the molecules are very small, at some point they disappear to our eyes. So they're so small we don't see them anymore, and we call that dissolving. Now, that is one reaction, but what's really happening at the microscopic level is that some of these molecules start clumping again, so they start becoming solid again. They're undissolving in a sense. So you have the dissolution that is occurring, and you have the reverse, which is the clumping that is occurring at the same time, at the same rate, at the same speed. So again, they're opposite reactions, and they cancel out because they occur at the same speed, and it makes it look to us at a macroscopic level, so to the naked eye, as if nothing's happening and the system is static. So that's the second example. Third example, the actual chemical equilibrium, so chemical reactions, are all the other chemical processes that are actually reversible. Not all chemical reactions are reversible, but some are. And that means that the rate of the forward reaction is equal to the rate of the reverse reaction. So because, again, they're happening at the same speed, we happen to not see a change. But at a microscopic level, particles are still being transformed from reactants into products, and the products are reverting back into reactants at the same speed, canceling out the two processes again and making it look as if nothing is happening to the naked eye. So I mentioned before that some chemical reactions are reversible and some are not. So an irreversible reaction can only happen in one direction. So for example, if you're burning something, well, you can't take the ashes and turn them back into the original substance. That just doesn't work. So that is an irreversible reaction. So the reaction at some point is complete. It stops. And it looks as if everything has stopped, right? So it stops when all the reactants are gone, if they're in proper ratios, or if you have one that's in excess, so you have too much of it, well, the reactant that you have less of will get consumed first, and you'll have leftover of the other one. An example would be if I mix an acid and a base in equal quantities, equal concentration, I'll have my neutralization, so I'll have my salt plus my water. Now let's pretend I put a lot of this, of the base, and a little bit of acid. Well, my acid will get neutralized. I'll have too much base. When will the neutralization stop? Well, when there is no more acid, and at this point I'll still have some base left, but it can't react with anything because I don't have any acid left. So I would have an excess of base in this case, making my whole solution more basic. In a reversible reaction, at first there is no equilibrium, so there's only the forward reaction that's occurring until the equilibrium kicks in and the reverse reaction starts occurring at the same time. So at first, my reactants react, and then at some point, some of the products start reverting into reactants. So this type of reaction is never complete, so we call it incomplete because it never stops. And the products keep turning back into reactants and reactants into products over and over and over again, as long as I don't touch the system. And in that case, if I don't touch the system, we'll say that the system is at equilibrium. So again, the rate of the forward reaction at that point equals the rate of the reverse reaction. They cancel out. We don't see a change, but again, at a microscopic level, there is a change occurring. There are two reactions actually happening at the same time. If we look in terms of change of concentration of reactants and products, how does this look like? Well, over here for the non-reversible reaction, my reactants start over here. So I have X amount of reactants. I have no product. So my reactants start reacting very quickly. You can see here the slope is very steep because I have a lot of reactants, a lot of collisions, so the speed is fast. So my reactants are reacting very quickly, and eventually it slows down. The whole reaction slows down until I have no more reactant and I'm at zero here. At the same time, those reactants that are being converted into products appear here in the blue line. So at first, because my reactants are reacting quickly, my products are also forming very quickly. And as the reaction slows down, my reactants are reacting less quickly. Well, the products are also being produced less quickly until, like I said before, there are no more reactants left. Well, then I'm not producing anything anymore, so the concentration stays constant at that point. In the case of a reversible reaction, the beginning is the same. My reactants will react, but they'll never reach zero because at this point over here, let's say about here, at this point over here, the concentration stops changing. Why? Because some of these reactants some of the products I should say, so these here are the products being formed. When I reach that point where the equilibrium is reached, so over here well, my products keep reverting back into reactants and my reactants into products. So my concentrations are stable, they're not changing anymore. Right? So neither are at zero. My reactants will never reach zero because my products start reverting into reactants. So it's always supplying matter on the reactant side of the equation. So because I never reach zero, this line will never touch my x-axis. It always stays stable at some point. So at the point at which your two concentrations become flat, stable, that's where we reach the equilibrium. Now, how do we write this in terms of chemical equation? This is a distinction between a reversible and a non-reversible. It's the double arrow. We're showing that we have a forward reaction and a reverse reaction, as opposed to a one-way reaction where we just use the single simple arrow. So what does this mean over here? If we break it down, it really means that my reactants, H2 and I2, are reacting together, becoming 2HI, and then my 2HI are colliding together, reacting together, reverting back into my two original reactants. Finally, 11.3, when do we have an equilibrium? What are the conditions to have an equilibrium? There are three. Obviously, we need to have a type of reaction that is reversible. As I said before, not all of them can be. We need to have a closed system. Why? Because if we keep losing matter, we're kind of upsetting the apple cart. So we keep changing the parameters of the reaction. And at that point, you can never have an equilibrium. It's like trying to stand on one leg. If somebody keeps pushing you, you'll never be able to achieve the equilibrium. You'll never be able to stand on that one foot of yours. So you need to have a closed system where nothing else exterior is affecting the system. And so that also implies that all the other parameters, may they be temperature, pressure, volume, pH, and whatever else, have to also be stable. Because again, if these keep changing, well, you're kind of modifying to some extent the reaction, and it'll never be able to attain that equilibrium. So you need a closed system, you need all your parameters to be stable, and you need, obviously, to begin with, a system that can, or a reaction that can be reversible. So if we look at examples here, which one do you think would be reversible? Which one would be complete? In other words, there's no equilibrium yet. Okay, it could be that will never be reversible. It could be that there's no equilibrium yet. In this case, I'm showing you two pictures, one with dissolved salt, one with a pile of salt at the bottom. So here we're not looking at a complete reaction, we're just looking at one that is at equilibrium and one that is not yet at equilibrium. So which one is presently at equilibrium? Well, if you said this one over here, I should go like this one over here, that is the correct answer. Why? Because over here, if you keep adding some salt, it hasn't reached saturation yet. So your particles of salt will keep splitting up into ions, so your salt will keep dissolving. Here you have reached saturation. So now you have little particles of salt at the bottom that are dissociating to become ions, and you have some of those ions that are reconnecting together and becoming solid again. And they're piling up here. So it looks as if your pile is not moving, it's not changing in size. Why? Because those that are splitting up do so as fast as those that are being formed. So there's virtually no change to the amount of particles in the pile of salt at the bottom of the beaker. So this system is at equilibrium. The forward reaction occurs as quickly as the reverse reaction. So that is example number one. Example number two, open or closed, which one is at equilibrium? So this one obviously is the open one, this one is the closed one. If you remember, we said that to have equilibrium, we need to have a closed system. An open system is not good. You keep losing matter as it is because there's gas fizzing out of it. So if you keep taking out matter out of the system can't reach that perfect balance whereby the gas would evaporate and some gas would condense, because whatever is evaporating is even leaving the system. So there's not enough gas here for some of it anyways to condense. So you can't reach equilibrium. So the only one that would be at equilibrium, or the only way it could be at equilibrium, is if it's closed. So for macroscopic versus microscopic, we can't really tell the difference between a system at equilibrium and one that's not at equilibrium, that is basically a complete reaction, because either way, to the naked eye, they both look like stopped or finished reactions. At the microscopic level, it's very difficult to actually observe the chemical reactions, and again, the particles, we won't see them moving around, vibrating or whatever. So even at the microscopic level, we can't really observe anything. The quantities, the concentrations are not changing. So this is not really something that we can rely on in order to determine if a system is at equilibrium or if a reaction is just a one-way reaction and has stopped, is finished. We can only have systems at equilibrium if we have a closed system and if the other parameters of temperature, pressure, and whatnot are all constant. So that's it for 11.1, 2, and 3. I'll see you around for 11.4.